Hi there. This is a video reviewing simple harmonic motion, an example quiz. And as you can see, you can get a 969 if you follow these directions. And to answer these questions, use KFES. No, and then it's supposed to be find, not fist, but I wrote that for a reason. Find, so you write down what you know, you write down what you're supposed to find, you write down the equations that you need to use, and then you solve it. And you will get a knuckle fist every Saturday if you don't pass physics. So that's how you remember what to do. KFES. So that's what we're going to do in this video. So first question, we're going to read what it says. A block of a mass 0.5 kilograms. So we write down that right away, since that's what we were told. That's the K. And it's saying that it's on a horizontal surface, and it's attached to a horizontal spring with no mass, with a spring constant of 50 Newton meters, or Newton divided by meters. And so, or newtons per meters. So the K equals 50 Newton meters. That's what we write next, because we just figured that out. Okay, the other end is attached to a wall where there's no friction between the block and surface. When the spring is unstretched, it's at 0 meters. So that means that this is equilibrium. So we write EQ to show that we know that's equilibrium. The block is pulled to 0.3 meters, and it's released so that it oscillates between negative 0.3 meters and 0.3 meters. What is the magnitude of acceleration and the direction of the net force when it's located at 0.3 meters? So right here, when it's right here. So we already did the first step, what you know. Now what are you supposed to find? It said acceleration, magnitude specifically, and direction of the net force. I guess we could just write an arrow to say direction. So now we need to figure out what equations we can use. Well, what equation has acceleration and force in it? Since those are the things we need to find. Well, that's Newton's equation. Sum of the forces equals mass times acceleration. We just have one force, so we can just write F. Now, if you rearrange that in terms of acceleration, A equals F divided by M. Now, this doesn't tell us what we need to know yet. So can we change the F or M based on what we're given? We only know M and K, we don't know F. Well, we know that F by Hooke's law is negative K times X also. So we can change it to that now. Now we can find acceleration because we know all three of those things. We know K is 50. We know X is 0.3 because that's it said at 0.3 meters. And then mass is 0.5. And when we plug that in to the calculator, we would get that the acceleration is 30 meters per second squared, really negative, but it only asks for the magnitude, so we only need to know 30. So that's why you need to pay attention to what it says. It says magnitude, so we don't need the negative. So we can cross out C and D because they don't show that acceleration is 30. So now we know that, but what about the net force? Well, the net force is, in this case, negative k times x, and that is negative 50 times 3, which would give us a negative answer. So we know that it's negative because of that. So the answer would be B. And another way to know is that the restoring force, which is what this is, it always tries to make the object go back to equilibrium, which we said was right here. So when it's right here, the force is going to act in the negative direction, which is left. So that was question number 1. So now that's how we followed those steps and we got that right. Now I'll try to go a little bit quicker now that we know the process. All right, 2 systems are in oscillation, and after you write down what you need to know, or what you know, you figure out that the this is the key sentence. The spring system takes twice as much time as the pendulum one. So 2 times the spring period equals the pendulum period. That's what we know. And now it's saying, what could we do to make TS equal TP? That's what it's asking. So now we already pretty much started out writing the equations. Now we can change it. So it's going to be 2 times 2 pi, and then the spring is m over k, and then this one is just going to be only 2 pi, and then L over G. So what could we do to make them equal each other? Either we would have to make this one go down or this one go up. That's the things that we could do. So let's figure out what these will do. So increasing the mass of the pendulum bob. Well, that's not going to do anything because m is not in this equation. So we can cross out A. What about B? Increasing the angle to which the pendulum swings. There's no angle in the equation, so it's not that. Decreasing the mass of the block and pendulum. If you decrease the mass of this, it will make the T go down. If you decrease the mass of this, it will make nothing happen. It won't make it go down, but it will make this go down, eventually making these equal. So that is the correct answer. Shorting the pendulum, that would make this even smaller. So that's why D is not right. Okay, now we're moving on to this problem. Okay, which equation defines the acceleration of this spring and block system? Well, we know, well, it doesn't really tell us anything, so we don't really, K is not what we do, but what about what we need to find? That's acceleration. What equations use acceleration? Well, this is kind of like on number 1. And then remember, we rearrange this to this, and then this. And that's the answer. So that one's pretty simple if you got the other one right. So there you go. Now this one, number 4, a pendulum consists of mass m at which is attached to a string of length L. It is displaced to the right by an angle theta. When the pendulum is released from rest, what speed does it have at its lowest point? So it's released from rest and we know it's going to go this way. So what do we know? Well, all it really told us are letters, so that doesn't really help us in this case. So, and we're trying to find the speed at the bottom. So that means we're trying to find V. And if you know about pendulums, at the bottom, it's also going to be the maximum velocity or the final velocity. So what do we use? Well, now we're trying to find equations. So what equations have L, V, and H in them? You would find out that they're your energy equations. And your energy equation says that the initial energy equals the final energy. At the top of the pendulum, we have potential energy, and we would change that to mgh as our equation. And then final energy is kinetic since there is a velocity. So that's 1/2 mv squared. Rearranging it in terms of v, we would get v equals the square root of 2gh. The m's would cancel out. But if you see, that's not in the answer choices. So don't get mixed up and think 2g, I didn't mean to say mg, but 2gl, no, that's not, it's supposed to be h. So we have to figure out what h is now, because h is not something that's in any of the answer choices. And using trigonometry, we would find out that h is L minus L times the cosine of theta. And that is a good equation to remember, because sometimes it can be tricky to derive that. And in certain situations, though, you would have to. But in most cases, it's good to just remember that. And so that means we can change h to that, because we know that's what h equals. So it's 2 times g times L minus L cosine of theta. And so that is your answer, and that is D. So that's the correct answer for that one. All right, next. Now we have a lot of different words. So that's why it's really helpful to write down what you know so you don't miss something. One end of a string is attached to a mass 0.5 kg. So we write that down. And then the other end of the string is secured so that the object rests and hangs from the string above the ground, as shown. The object is pulled to an unknown height. That's a key thing to know, unknown height. So we can write h equals question mark, because we don't know what that is. You'll see why that's useful to know in a minute. The object is then released from rest. The speed of the pendulum in the figure is 2 meters per second. And since that is at the bottom, we know that's our final or maximum velocity. And it undergoes simple harmonic motion. What is the change in gravitational potential energy? So change in UG equals what? That's what it's saying. And considering the information given. Now, once again, now we need to know the equations. So how do you find change in potential energy? Well, we know that it is final minus initial. But the problem is, we don't know the height. Remember, they said that. And they put in this 1.5 meters to try to throw you off. You might think, oh, that's the height. No, the height is something that's like right here, and we don't know what it is. So, and since always at the bottom, when the pendulum reaches the bottom, it is 0. The gravitational potential energy is 0. So the final U is 0. So we know that the change in gravitational potential energy is just going to be the initial gravitational energy. But we don't know that, do we? But using conservation of energy, we know that that would have to equal the final energy, and the final energy is kinetic. That's just using this equation. The final energy is kinetic. So we then know that the initial potential energy is equal to the final kinetic energy, which is also equal to the change in gravitational potential energy. So Therefore, we can say this. And then, to save some time, I'm not going to write it all out, but you would find that the answer is 1 joule, plugging everything in that you know. So that one was a little bit trickier, but it's just thinking about all the equations you know and writing down what you know. So that's the key to getting it right. All right, now let's go on to number 6. Okay. This figure shows a pole with a spring around it and a 0.1 kg block. So that's the mass. Let's write that down since we know that. And oh, that's kind of glitchy to read. And it's saying that the frequency is 5 hertz. And it is saying, what is the spring constant? So as you can see, sometimes things don't matter what they say. They're just kind of random things. So that's what we're trying to find. Now we need to figure out what equations to use. Well, how can we find spring constant knowing those things? Well, we know that we can find the spring constant if we know the period. Also, if we knew the force, but that doesn't help us in this one because we know the period, or not pendulum, spring equals this. We know that. So we need to first find this, and then we'll be able to find this. So you break it into steps. So first, we need to know that the frequency equals 1 divided by the period. And the period also equals 1 divided by the frequency. So that means that 1 divided by f equals this. So we can plug that in. So 1 over f, which is 5, equals 2 pi times the square root of mass 0.1 divided by what we're trying to find, k. Now we have to isolate k and get it by itself. So once you do that, assuming you have good algebra skills, you would find that it equals, k equals approximately 100 Newton per meter. And that would mean A is the answer. Okay, now 7 and 8 are pretty simple, and I'll be able to do these quick. So it's saying, what shows the kinetic energy? This isn't really one where you solve for something, so you don't necessarily have to do the same steps because it's just graphs. But it's saying, what is the kinetic energy? Well, we need to know that the equation for kinetic energy equals this. Velocity is squared. So if you know algebra, that means that it's going to have to be a parabola. So either like that or like that. So we can already cross out A and C. So is it B or D? Well, we know that at equilibrium, velocity is maximum. So that means in the middle, it will be up high. So that means it's going to be D. Okay. Now, 8 is the same, except for now it's asking for potential energy. And the potential energy of a spring, which is what this is, that equals 1/2 times kx squared. X is squared, so once again, it's going to be a parabola. So we can cross out A and C, but is it B or D? Well, we know that displacement, or X, is maximum at the end just by seeing that picture. So that means that it's going to be highest at the beginning and end. So the answer is B. Okay, now number 9. Two oscillating systems, a spring mass and simple pendulum, undergo simple harmonic motion with an identical period t. So that means that so far they equal each other. If the mass of the system is doubled, what will happen to the new period? So this is called factor of change. And in factor of change, you can do it a way more complicated way, and you'll have to like do ratios. But what you need to do is only change what thing it's telling you about. So it's saying what happens when we change the mass. So that's the only thing we're changing. So don't change anything else. Just make everything 1 because it's going to be constant. And that will show you specifically the change already. So we start out with the spring to see what would happen to it. The period is 2 pi times mass divided by spring constant. So we make everything 1. So 2 pi, we'll just make that 1. But since mass is doubled, we'll make that 2, and then we'll make spring constant 1 because it's not changing. So when you simplify that, that is square root of 2 of the t. So that's saying that it's changing by that much. Now, for the pendulum, same thing. But there is no mass in the equation for period of a pendulum, so it does not change. So the answer is C, or B, sorry. Yeah, so that's what you do. You just put a T there beside whatever it is. Okay, now number 10. Now we're trying to, well, it tells us that the length of a pendulum is, so L is 1 meter. On a hypothetical planet X, so that means that gravity is not going to be 10 like it usually is. What is the surface gravity if the period is 4 seconds? And so we're trying to find what G is. So we use the equation that we know, and we would plug in 4 for the period, and then 2 pi times L is 1 divided by G. Using your algebra skills, then you would find out that it is 2.5 meters per second squared. Okay, now we're selecting 2 answers. One's like this. Always make sure you see that it says that. Okay, what is true when it reaches its maximum displacement? So it might be helpful to draw a picture. Well, this is just a spring, for example. Let's say this is equilibrium, and where it is its max displacement. So what's true? Is acceleration 0? No. And this is just knowing your stuff, basically. Is kinetic energy at a max? No, because velocity is 0, so how could it be at a maximum? Velocity is 0, yes, that's true. I just said that. And then potential energy is at a maximum, yes, because that's based on the change in x being at a maximum, and since it is, also the potential energy will be. And those were multiple choice questions. Now we have free response questions too, and we gotta do things right to get all the points. Okay, so still you use the same process on these. Okay, so what do we know? Block P has a mass m. Well, that's already labeled, so we don't necessarily have to write that down. It's a frictionless surface attached to it. So there's no values here. So there's not really anything to write down, but just read what it says. So assuming you already read it, it is saying determine the numerical value of the ratio. Well, we have to pay close attention to what it says. Numerical value, that means no variables allowed. Just abbreviate. Well, never mind. No variables. And for the ratio of the period of PQ divided by the period of P. So that might seem hard, but it's not. So really, we're just trying to find period of PQ divided by period of P. They are both springs, so we know it's going to be 2 pi times mk, but PQ, that includes both of these. They have masses 2m and m, so it's going to be 3m for the mass on here. That's something important. And then here it's just P, so that's going to just be M over K. And what you can do is you can cross out the 2 pi's. So remember, no variables. So we're going to try to figure out how to get rid of the m's and k's. So then we know that we can just put that all under one radical, and we can have 2m, and then yeah, wait, it would be this. And then when you multiply by the reciprocal right there, it's going to be 3m over k, and then the reciprocal is k over m. And the k's cancel out and the m's cancel out, and we're left with just square root of 3. That doesn't have any variables in it, and that's the correct answer. So that's good. All right, now that was just 12. That was only a 1-part thing. Now we got this last question, free response, but it has a lot of parts. So the thing that's not so good about these is if you mess up one thing, it might mess up all your answers. So, but after reading this, just skipping the steps that we already know, you would find out the following: that the mass is 4 kilograms, that the spring constant is 650, and then you would find out that the change in y when it falls is 0.8 meters. And then you would also find out that the change in x during the fall is 1.2 meters. Now, first it says calculate the time elapsed the instant that it leaves the table and strikes the floor. So you might be thinking, okay, time, how do we find time using those things? Well, time is in period, but that's not going to be helpful because that doesn't have to do with when it leaves the table. That's only for when there's springs, things in simple harmonic motion. When it leaves the table, that's longed horizontally. That's something to take note of. So that means we need to use kinematics. And kinematics, we would end up using the equation final y equals initial y plus initial velocity times t plus 1/2 acceleration times time squared. Okay, well, how do we find the time? So we know the final y is 0 because it's falling down, and the initial y is 0.8. The initial velocity, when it leaves the table is not 0, but it is 0 when it's at the maximum displacement. And so the initial velocity there would be 0 for this case. So we can cross out that term since it's 0. Same thing there. And then plus 1/2 times acceleration. What's acceleration? Well, whenever it's falling down, the only acceleration is gravity. How do we know this? Well, Newton's equations. The only force is force of gravity when it's falling, assuming no air resistance. So how do you find A? A would end up being force of gravity divided by mass. And we know that force of gravity equals m times g. So we cross out the m's and it's just g. So we can use -10. We have to use -10 in kinematics. And then t squared. Then we would find out that the time for when it fell was 0.4 seconds. That is that part, all right? Let's move on. And always what happens if you get one thing wrong, then it's going to make your other answer wrong, if it's A, B, C, D. So what is the initial velocity in which it left the table? So remember, we said it was 0 above, but this is saying when it left the table, exactly when it left the table. So how do we find that? Well, we can look at what equations we use and kinematics again, that's what we have to use. So we'll use the one that says this. Well, kind of the same one as last time. But we'll just use X this time. So then we have, oh, wait. Yeah, sorry. This is what I should have explained above here. So the reason why our velocity is 0 right here is because it's in the y direction. And there is no velocity in the y direction at the top of a horizontally launched thing, only x. So that's what it's talking about right here, x direction. So that's important to note. Sorry about that. Okay. So this is 0. This is 0 because acceleration is 0. Or yeah, okay. So then we just figure out that it's this. And x is 1.2 time, we got that in the last answer. That's what I was talking about. If you got the last answer wrong, you would get this wrong too. So the initial velocity is 3 meters per second. Okay. And in the x, that's something important to know, because in the y, it's 0. All right, calculate the distance x that it was compressed. Let's see. So now we're talking about the compressed part. So think about simple harmonic motion again. Well, how do we find that? Well, we know Hooke's law. All right, but we don't know force, but we do know that force equals mass times acceleration. And rearranging that, we would get this. Oops. And distance, we're assuming that it's the magnitude, because distance is a scalar, not a vector, so we don't need negative. So we don't need, so we don't need to make this k negative anymore. So now we say, oh, sorry. See, this is why you sometimes do the wrong thing. This is the wrong thing to use because we did not know acceleration. Sorry about that. So sometimes you do the wrong thing. Okay, no. All right, I just did the wrong thing. Okay, let's try that again. All right. Instead, we actually can use this using a different equation that still involves what we know, which is kx and v. And we just found out v in the last one. Oops, that's the other way around. Initial energy is this. All right, and plugging in our values that we knew, I'm not going to take time to do that, but we would get this. And anyway, since x is squared, that's why it ends up being positive, but good that it is because that's a scalar. So that's the answer for that part. And then the last thing, what is the maximum force? Now we find the force. So now let's go back to Hooke's law. And oh, that's pretty easy because all we have to know is this. I did it again. We don't need to rearrange it into x. I don't know why I was doing that. Sorry. K equals 650. And then x we just found was 0.23. But this time we need to realize something. We actually do need to put a negative in here right now because compressed. Let me scroll back up here. So it's compressed, and when it's compressed, it always tries to make it go. The force always tries to make it go to where it's equilibrium. I said that on question 1. So that's to the right. So it's positive, and also the displacement is negative when it's compressed because it's before the equilibrium point. So that's why we have to make it negative at that part. Before in C, it's positive because it said distance and not displacement. That's something to take note of. That's why you have to know the keywords. And that would make the restoring force or the maximum force 150 newtons. And with that, that is the end of this review video to how you can get a 969 on your simple harmonic motion quiz that also involves all the other units. Well, I don't think there's any circular motion or unit 7. So, okay. Thanks for watching, and that'll be it.